Preparing for an interview preparation at Skyroot Aerospace interview. You've reached Candy Mentor, and this video is for you. We'll walk through 25 key questions you're likely to face. For each question, you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. Why do you want to work at Skyroot Aerospace? And what role do you see yourself playing in a launch vehicle program? I want to work at Skyroot because launch vehicles combine deep engineering, national impact, and startup speed execution. I'm especially excited by teams where design, testing, and failure analysis are closely linked. My role would be to bring strong fundamentals, disciplined implementation, and ownership to mission-critical subsystems. Whether I work on software, avionics, structures, or analysis, I would focus on reliability, traceability, and decisions backed by data, not assumptions. While answering, connect your motivation to private space launch, mission ownership, safety-critical engineering, fast iteration, and Skyroot's launch vehicle focus. Mention relevant projects, teamwork, learning speed, and comfort with high accountability. Question 2. How would you explain the major subsystems of a launch vehicle to a non-specialist? A launch vehicle is basically a coordinated stack of subsystems. Propulsion generates thrust. Structures carry loads. Avionics act as the brain, and GNC keeps the rocket on the desired path. Power systems feed electronics. Telemetry sends health data to ground. And separation systems safely detach stages. The payload interface protects the customer payload. The key point is integration. Every subsystem must work together under vibration, heat, acceleration, and strict timing constraints. Make sure to cover propulsion, structures, avionics, guidance navigation control, telemetry, power, stage separation, payload interface, and ground systems. Keep the explanation simple, but show systems-level understanding and interdependency. Question 3. What are the key differences between solid, liquid, and cryogenic propulsion systems? Solid motors are simpler, storable, and high thrust, but once ignited, they are difficult to throttle or stop. Liquid engines allow better control, shutdown, and sometimes restart, but need pumps, valves, tanks, and complex plumbing. Cryogenic propulsion uses very cold propellants like liquid oxygen or hydrogen and can offer high performance, but storage and thermal management are hard. The right choice depends on mission requirement, reliability target, manufacturing capability, and cost. In your answer, compare thrust control, complexity, storage, performance, cost, restart capability, safety, and use cases. For aerospace startups, highlight manufacturability, testing, reliability, and mission trade-offs. Question 4. How would you design flight software for a launch vehicle? I would design flight software around deterministic state machines and time-critical control loops. Sensor acquisition, navigation, guidance, actuator commands, telemetry, and fault management should be modular but tightly synchronized. I would avoid dynamic behavior where possible, use bounded memory, strong interface definitions, and extensive logging. Every requirement should map to tests, including unit, integration, simulation, and hardware and loop tests. In flight software, predictability matters more than cleverness. Be sure to mention modular architecture, deterministic timing, sensor interfaces, control loops, command handling, redundancy, state machines, fault detection, logging, testing, and certification-style traceability for safety-critical behavior. Question 5. What makes real-time embedded systems different from normal application software? In normal software, a late response may be annoying. In real-time embedded software, it can be a failure. The system must produce correct outputs within strict timing deadlines. That changes design choices. Fixed memory allocation, predictable scheduling, interrupt discipline, watchdogs, and careful hardware interaction become essential. I also think about worst-case execution time, not average performance. For a launch vehicle, timing, reliability, and graceful fault handling are part of correctness. While answering, focus on deadlines, deterministic behavior, interrupt handling, resource constraints, scheduling, watchdogs, memory limits, hardware interaction, failure impact, and why correctness includes timing, not just output. Question 6. How do you approach sensor fusion for navigation in a rocket? Rocket navigation relies heavily on IMU data because it is fast and self-contained. Accelerometers and gyros estimate position, velocity, and attitude, but they drift due to noise and bias. Sensor fusion, often using Kalman filter-style estimation, combines measurements and models to reduce uncertainty. I would pay close attention to coordinate frames, timestamp alignment, calibration, and outlier rejection. The estimator must be validated with simulations, lab tests, and flight-like vibration environments. Make sure to cover IMU, accelerometers, gyroscopes, GPS, GNSS if available, filtering, bias correction, noise, sampling rates, coordinate frames, redundancy, and validation using simulation or test data. Question 7. Explain how control systems are used to stabilize a launch vehicle during ascent. A rocket is naturally unstable during parts of flight, so control systems continuously correct its attitude. Sensors estimate orientation and angular rates. The controller compares them with the desired trajectory, and actuators like thrust vector control apply corrections. A PID controller is a simple example, but launch vehicles may use more advanced control laws. The design must account for delays, structural flexibility, actuator saturation, and changing mass. Simulation is essential before hardware testing. In your answer, talk about attitude control, feedback loops, PID or modern control, actuator limits, thrust vector control, sensor feedback, stability margins, delays, and testing through simulation before flight. Question 8. What is max Q and why is it important in launch vehicle design? Max Q is the point of maximum dynamic pressure during ascent, where aerodynamic loading on the vehicle is highest. Dynamic pressure depends on air density and velocity, so it rises as the rocket accelerates, then falls as the atmosphere thins. This point drives structural sizing, fairing design, and control constraints. Vehicles may throttle down or shape trajectory to manage loads. It is a classic example of propulsion, aerodynamics, structures, and guidance interacting. Be sure to define dynamic pressure. Explain why aerodynamic loads peak. Discuss throttling or trajectory shaping, structural margins, vibration, fairing loads, and coordination between propulsion, structures, and GNC teams. Question 9. How would you design and verify a stage separation sequence? Stage separation must be treated as a mission-critical sequence, not a single command. I would define preconditions such as burn completion, attitude limits, and safe dynamic conditions. Then the software triggers separation devices, confirms events through sensors, and commands the next stage only after valid confirmation or safe fallback. Verification needs mechanism tests, electrical checks, timing analysis, simulation, and hardware-in-loop testing. The design must prevent recontact and produce clear telemetry for analysis. While answering, cover separation logic, pyrotechnic or non-pyro mechanisms, timing, sensor confirmation, safe states, collision avoidance, sequencing, redundancy, ground testing, simulation, and telemetry evidence for post-flight analysis. Question 10. What telemetry would you prioritize during a launch, and why? I would prioritize telemetry that helps confirm mission health and diagnose failures quickly. That includes propulsion pressures and temperatures, take conditions, battery voltage, avionics status, IMU and navigation estimates, actuator commands versus feedback, separation events, and flight software state transitions. Since bandwidth is limited, critical low-rate health data should be guaranteed, while high-rate data can be selective or buffered. Good telemetry is designed before launch, not added after anomalies. Make sure to mention health monitoring, propulsion pressures and temperatures, IMU data, battery voltage, actuator states, event markers, software states, bandwidth limits, compression, prioritization, and ground visibility. Question 11. How would you implement fault detection, isolation, and recovery in a launch vehicle subsystem? I would start by identifying credible failure modes and defining detectable symptoms for each. Fault detection can use thresholds, consistency checks, timeout monitoring, and sensor voting. Isolation narrows the cause, such as distinguishing a bad sensor from a real pressure drop. Recovery may switch to redundancy, reset a component, use degraded mode, or abort if safety requires it. The hard part is tuning logic to avoid both missed faults and unnecessary mission termination. In your answer, discuss thresholds, model-based checks, sensor voting, timeout detection, safe modes, redundancy management, graceful degradation, false positives, logging, and balancing autonomy with mission continuation. Question 12. What embedded C or C++ practices matter most for safety-critical aerospace software? For safety-critical embedded software, I avoid surprises. That means no uncontrolled dynamic allocation during critical operation, careful pointer use, bounds checks, explicit initialization, and no dependence on undefined behavior. I use static analysis, compiler warnings, code reviews, and standards like MISRA principles where applicable. Hardware registers need careful volatile handling, and interrupt shared data needs protection. The goal is code that is boring, traceable, testable, and predictable under worst-case conditions. Be sure to cover deterministic memory, avoiding undefined behavior, static analysis, MISRA-style rules, bounds checking, volatile usage, interrupt safety, clear ownership, code reviews, and test coverage. Question 13. What is priority inversion in an RTOS, and how would you prevent it? Priority inversion happens when a high-priority task waits for a resource held by a low-priority task, while medium-priority tasks keep running and delay the low-priority task from releasing it. In avionics, that can break timing guarantees. I would prevent it using priority inheritance or priority ceiling protocols, short critical sections, careful mutex design, and avoiding unnecessary shared state. I also verify worst-case blocking time during scheduling analysis, not just during testing. While answering, explain high, medium, and low priority tasks, shared resource locking, priority inheritance or ceiling protocols, mutex design, bounded critical sections, and why it matters in real-time avionics. Question 14. How do you choose between communication protocols like CAN, UART, SPI, I2C, and Ethernet in avionics? I choose the protocol based on data rate, determinism, distance, noise environment, and fault tolerance. SPI is fast for short board-level communication. I2C is simple for low-speed devices. UART is useful for simple serial links. CAN provides robust multi-node communication with arbitration and error handling. And Ethernet offers high bandwidth for data-heavy systems. In avionics, electrical robustness and predictable behavior matter as much as speed. The best protocol matches the subsystem's risk and timing needs. Make sure to compare bandwidth, latency, distance, topology, noise immunity, determinism, complexity, error detection, hardware support, and use cases like sensors, actuators, telemetry, and ground testing. Question 15. How would you build a hardware-in-the-loop test setup for flight avionics? A hardware-in-the-loop setup connects the real flight computer to simulate its sensors, vehicle dynamics, and actuator feedback. The goal is to make the software believe it is flying, while we control scenarios safely on the ground. I would include timing-accurate IMU feeds, command interfaces, telemetry capture, and fault injection for sensor dropouts or actuator failures. Automated scripts can replay nominal and off-nominal missions. HIL is powerful because it tests integration, not just algorithms. In your answer, include real flight computer, simulated sensors, actuator models, timing fidelity, fault injection, telemetry capture, automated test scripts, scenario replay, and comparing outputs against expected mission behavior. Question 16. How do material selection and manufacturing constraints affect rocket structural design? Rocket structures are driven by mass efficiency, but they still need strength, stiffness, thermal resistance, and manufacturability. Aluminum alloys, steels, titanium, composites, and additively manufactured parts each bring trade-offs. A composite may save weight, but complicate inspection and joining. Additive manufacturing can reduce part count, but needs process control and qualification. I would select materials based on load cases, environment, inspection capability, production repeatability, and total mission risk, not just theoretical strength. Be sure to discuss strength-to-weight ratio, thermal loads, vibration, fatigue, composites, metallic alloys, additive manufacturing, inspection, manufacturability, cost, repeatability, and safety factors in flight hardware. Question 17. Explain specific impulse and why it matters for rocket performance. Specific impulse measures how effectively a rocket engine uses propellant, usually expressed in seconds. Higher ISP means more thrust per unit propellant flow, which improves delta V and payload capability. But it is not the only metric. An engine with high ISP may be complex, expensive, or low thrust. For launch vehicles, the best propulsion choice balances performance, reliability, manufacturability, cost, and mission profile. Efficiency matters, but usable engineering matters more. While answering, define specific impulse clearly. Relate it to propellant efficiency, thrust, mass flow, delta V, mission capability, engine comparison, and why higher ISP is not always the only design goal. Question 18. How would you approach trajectory optimization for a small launch vehicle? I would start with the target orbit, payload mass, vehicle constraints, and safety corridor. The trajectory must balance gravity losses, aerodynamic loads, engine limits, staging conditions, and guidance feasibility. Optimization variables may include pitch program, throttle schedule, staging time, and angle of attack constraints. I would first build a physics-based simulation, then optimize within realistic margins. A trajectory is only useful if GNC can fly it and structures can survive it. Make sure to cover mission constraints, payload orbit, staging, aerodynamic loads, gravity losses, steering losses, engine limits, safety corridors, optimization variables, simulation, and validation against flight constraints. Question 19. A static fire test shows unexpected pressure oscillations. I would first verify the data quality, sensor calibration, sampling rate, timestamps, and whether multiple sensors agree. Then I would analyze frequency content to see if the oscillation matches combustion, feed line, valve, or structural modes. I would correlate pressure with temperature, thrust, valve commands, and acoustic data. The next step is isolating hypotheses through simulations, inspection, and controlled tests. I would not jump to redesign until measurement error and operating conditions are ruled out. In your answer, discuss data review, sensor calibration, frequency analysis, combustion instability, feed system dynamics, valve behavior, structural coupling, repeatability, root cause isolation, and safe next test planning. Question 20. How would you design a reliable power system for avionics during launch? I would begin with a load budget for every avionics component across all mission phases, including peak currents and margins. The power system needs reliable batteries, regulated rails, protection against brownouts, proper grounding, EMI control, and health telemetry. Critical loads may need redundancy or isolation, so one fault does not collapse the bus. I would verify performance under vibration, temperature, and transient conditions. Power design is unglamorous, but many failures start there. Be sure to cover battery sizing, voltage regulation, redundancy, load budgeting, inrush current, EMI, brownout protection, health monitoring, grounding, thermal limits, and verification under vibration and temperature. Question 21. How should configuration management work for flight software and mission data? Flight software needs strict configuration control because a small change can alter mission behavior. I would use version control, tagged releases, reproducible builds, and clear separation between development, test, and flight builds. Mission parameters should be reviewed and baselined like code. Every release should link requirements, change requests, test results, and approval records. If an anomaly occurs, the team must know exactly what software and configuration flew. Traceability is a reliability tool. While answering, focus on version control, release baselines, requirement traceability, parameter management, build reproducibility, review approvals, test evidence, rollback strategy, and separating development builds from flight-certified builds. Question 22. What cybersecurity or safety concerns apply to aerospace ground and flight systems? Aerospace systems need protection against unauthorized commands, tampered software, and compromised ground infrastructure. I would use strong access control, command authentication, network segmentation, secure build pipelines, audit logs, and controlled software updates. Safety interlocks are also critical, so operational mistakes do not become hardware damage. Security should not block real-time mission operations, but it must be designed into procedures and tooling. In launch systems, cyber risk and safety risk are connected. Make sure to mention command authentication, access control, secure update processes, network segmentation, logging, insider risk, supply chain trust, safety interlocks, and balancing security with operational reliability. Question 23. How do you work effectively with propulsion, structures, avionics, and software teams on one vehicle-level problem? Vehicle problems rarely stay inside one discipline, so I start by clarifying interfaces and shared assumptions. If avionics needs a sensor moved, structures may care about mounting loads, and propulsion may care about thermal exposure. I would use interface control documents, design reviews, and joint test plans to avoid surprises. When teams disagree, I prefer trade studies with data, not opinions. Good cross-functional work is about making dependencies visible early. In your answer, highlight interface control documents, shared assumptions, trade studies, clear communication, test planning, system-level thinking, requirement ownership, design reviews, and resolving conflicts using data. Question 24. Tell me about a time you solved a difficult technical problem with incomplete information. In that situation, I would explain how I separated known facts from assumptions, then attack the biggest uncertainty first. For example, if a system failed intermittently, I would reproduce it, add logging, isolate variables, and test hypotheses one by one. I would keep stakeholders updated on risk and next steps. The important part is not pretending to know everything. Strong engineering under ambiguity means reducing uncertainty with disciplined experiments and clear communication. Be sure to structure the story using situation, constraints, actions, trade-offs, validation, and result. Emphasize first principles thinking, experiments, stakeholder communication, and how you reduced uncertainty step by step. Question 25. If you discover a potential issue close to a launch or major test deadline, what would you do? I would never hide or minimize a potential flight or test issue, because schedule pressure cannot override safety. First, I would gather evidence quickly: logs, measurements, reproduction steps, and affected configurations. Then I would escalate to the right technical leads with a clear risk statement and possible mitigations. If the issue is low risk, we document and proceed. If it threatens mission or hardware safety, we stop. Mature teams make hard calls early. While answering, focus on safety-first judgment, transparent escalation, evidence gathering, impact analysis, risk classification, decision logs, teamwork under pressure, and avoiding both panic and concealment. If you are still with us, congratulations. You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.